Welcome to qnawire.
Hi there. So over here we're asked to graph the energy for the H2 plus cation corresponding to a certain equation. In this case, the equation is not provided, so we're going to use the one that we derived in the previous question, assuming that the wave function is going to be a linear combination of hydrogen atom ground state functions located at the different positions of the protons. Recalling that our system is going to have two protons and an electron, let's say proton 1, proton 2, and the distance r1 and r2. Okay, so the result from doing that is going to be that the total energy for our system is going to be equal to, in terms of our quantity x, which corresponds to r divided by the Bohr distance a0, this is going to be equal to 1 plus 2 times d plus minus j divided by 1 plus minus s, which is the overlap, multiplied by E naught minus 2 over x multiplied by E naught. Recall that the values for d, j, and s were calculated in a previous question. In this case, we can rewrite this expression as minus a certain function that depends on r divided by A naught, which is our value of x, multiplied by E0. And after finding doing all of the substitutions, this energy is going to be equal to, we're going to open a very big parenthesis. This is going to be equal to 1 minus 2 over x, a fraction that is going to contain 1 plus x, multiply e to the minus 2x, plus minus 1 minus 2x squared divided by 3 times e to the minus x, and all of this divided by 1 plus minus 1 plus x squared over 3 multiplied by e to the minus x. And all of this is going to be multiplied by the value for e0. So now the only thing that we need to do is to do the graph corresponding to this. The shape of the graph is going to be the following. I'm going to write it down, energy as a function of x, and the shape is going to be, actually, you can actually do the graph properly, but for e plus, or the function f plus if you want, this is the shape that you're going to arrive, and for f minus, the anti-bonding state is going to be this one over here. Now, in order to find the bond dissociation energy, what we need to take is the difference between the minimum and the energy corresponding to r equal to infinity. At r equal infinity, what essentially we're going to have is an hydrogen atom plus a proton at dissociation. And in order to find the minimum, what we need to do is to take the derivative of our energy with respect to this value of x, and this derivative needs to be equal to 0. The solution that we find for this is that the value for x is approximately equal to 2.5 for the construction that we found here. And the energy at this point is going to be approximately minus 1.13. Of course, this is all going to be in terms of E0, and the value for A0. So since x is equal to 2.5, that means that the value for r, the interatomic distance, is going to be 2.5 times A0, or the equilibrium distance corresponds to 1.33 times 10 to the minus 10 meters, which is 1.33 angstroms. Now, for the binding energy, or the bond dissociation energy, this is going to be equal to the value for the energy at equilibrium, this value for E plus that we got, minus the value for E naught, which is going to be minus 1.13 E naught minus the value for E naught. Oh, sorry, over here it was F plus, so that the value for energy plus at equilibrium is equal to 1.13 E naught. So this is positive, sorry about that, little mistake. So we get that the bond dissociation energy is then 0.13, the value for E naught, which is approximately minus 1.77 electron volts. Now, this of course depends on the wave function that we employed as ansatz. In this case, I used a very common approach, which is considering a linear combination of the ground state functions for hydrogen atoms between both of the located at both of the protons for our system, and these are the results that we get. This is not exactly the experimental result, but it is quite close, and this is the most common result for that you're going to be able to find in most quantum chemistry textbooks. So, with that, it would be all. Thank you very much, and have a good one.